Hello, everybody, and welcome to another final projects presentation ceremony. Hello, today we are in the last final project presentation ceremony of this year 2024, but it's going to be a very good session for sure. We have very varied presentations today. We have a very interesting menu. Each presentation is going to be about different topics using different robots. So I'm sure that you are going to enjoy all of them. And yeah, so without further ado, I'm going to already introduce the first presentation, which is going to be delivered by Sanghoon Lee. Let me introduce him, and his presentation is titled Cafeteria CleanerBot Table Picker. So he is going to be working with our TurtleBot 4 that we have in the cafeteria and making sure that the cafeteria environment stays as clean as possible by automating a table picker system that he's going to introduce and explain right in a moment. So yeah, Sanghoon, you can go ahead. It's all yours.
Okay, thank you. My project is just introduced the Cafeteria CleanerBot table picker. I will introduce a solution and CI/CD implementation of my project. Okay, the table of contents are like this: overview and the automated system, and create web application, Docker and CI/CD pipeline, and wrap up. The problem, description of the problems. My problem is that set up an automatic system to find and pick up a trash table in the cafeteria, and to take it to the back room and create a web application to command the robot, and containerize using Docker and little DevOps procedure. I will implement it simulation first, and then operation in real lab. I also would like to show you to simulation and real lab together. First, okay, overview. Actually, this is the overall development architecture for me. The construct ID in Robotics, I develop a solution and testing in simulation, and also operation in real life. I also focused on the CI/CD pipeline. There is some issue. I will explain it later. But so I have to set up in local PC for Jenkins and Docker. So this is my overall dev architecture. Then I would like to show demo first. This is the demo in simulation environment. So I would like to show you my solution. Using this video clip. It will take about 4 minutes. This is the simulation environment. Left side is simulation, and I visit. During the demonstration, I will connect the real lab and prepare for the next demonstration, which is in real time on real robot. That's your simulation. This is the pickup point location location, the robot is go on the table. Yeah.
So can you explain a little bit what's going on?
Yeah.
Sanghoon?
Okay. Yeah. Then it go out from the obstacle area, then go to the corridor position through the put down location. Yeah. And the 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 logic will be explained in later. This is the corridor position one, and then go to put down position. Then put down the table and go out from the table to the table. Then go back to home position. Yeah. Yeah, done. This is the demonstration in the simulation environment. Next, I will uh, demonstration it in real lab. So in real lab, I will simulate it, demonstrate it like this flow. First, and go to the pickup location number one, and then go into the table, and then go back, go out from the obstacle area to here safe zone, and then put down location through the 2, 3 corridor position, and then if when it arrives at put down position, then put down it and go out from the table, and then go back home. Okay, let me connect the real robot.
Right. So you're going to connect to the real robot now, right, Sanghoon?
Yes, that's
Okay.
yeah, right.
So Sanghoon right now has opened a project. In case that somebody in the
Yes.
audience doesn't know what this is
Okay.
an environment in the cloud, okay, which Sanghoon can use, and from where he can connect to a real robot that we have here in our offices in Barcelona. But you are right now in Korea, right, Sanghoon?
Yes, yes, right.
Yeah.
It's the midnight. Yeah, she's the robot. Yeah.
Okay, so this is live here in Barcelona. Okay, what we are seeing here in the
Yes,
cameras.
right. Yes. Since it is a remote connection environment, so the demo will be executed in the area visible to the camera.
Okay.
Please understand. And first, I would like to install some packaging, which is not included in default IDE. So this one, and for the charging, I have to some packaging for the send the message to the docking message.
Okay.
So
So these are some additional dependencies.
yes, right.
I can see you are going to need many shells.
Yeah, right. Then I will launch the navigation system,
Okay.
the path planner server with the localization server.
Okay. So what is? Can you tell us what is this
Yeah,
that has just
yeah,
appeared?
yeah. Okay, this is the navigation
Okay.
system, so we can see the map and the in the IPs. Uh, I can use the navigation stack to move the point waypoint.
Mm-hmm.
Then I will launch my application, and this is the approach the table.
Mm-hmm.
Okay. Then this is the trash table mover action server.
Okay.
I think okay. the the filter map is not started off in navigation system. I will restart it. Oh yeah, this is right.
Okay. So can you tell us, Sanghoon, what are those
Okay.
purple blocks that appear in the map?
Yeah, this the color is the mask area for the when the planar server is planned to pass
Mm-hmm.
to avoid some reason like this so far.
Mm-hmm.
This is some the robot can misunderstand the uh, calculate the path. So
Mm-hmm.
I prevent it with some in mask.
Okay. Okay.
So yeah,
So areas where the robot is not allowed to go through.
yes, yes, right. This is the ROS bridge to web and WebSocket bridge and the TF to web republisher to trace the TF. It will show in the web UI.
Okay. So this is for being able to use the web with ROS, right?
Yes, right. Then I will connect the web server and ROS bridge. Here is the address. I will copy it to the
Okay.
here is the through the gateway. I will connect the web server in my application in construct ID, and then I will connect to ROS bridge.
So this is a web page that you have created, right?
Yes, right. Yeah. I can select the real robot and simulation, but this is the real robot, so I select the real robot and connect. Then connect the robot. This is the map. This is the tab, the robot. Then I will send the command from this here, the clean trash table 1. Then robot will go to the picker position 1, then find the table, and then lift up its table to the down position. Okay, then actually this will need to go down. Okay, then ready to execute. I send the action, the clean trash table 1, but a little bit confusing. The table is some different location with a map. Anyway, I can start. Connect. Maybe it some timeout. Okay, then push clean table 1. Yeah, the path is the calculate. So the robot will go to the loading position.
Okay. It's not moving, right? For some reason.
Maybe the DBS tag is not working. I will send the go to pause, but the navigation is not working.
Yeah.
Maybe. Okay.
One of the cameras is paused though. I don't know about the other, but the one in the left at least.
Okay.
Okay.
One is the. I will the reposition the table and then start the program. Okay.
Okay. Or you can try running
myself.
or sending a manual goal through RBs or something to make sure that.
I will tele joystick
Okay.
in this web application.
Okay. Yeah, just to make sure that the robot can move properly, because maybe there's something
Yeah.
happening there.
Yeah. Mm. I think the robot is not moving.
Okay.
Someone helped me to reboot the robot. I think
Okay.
the robot is not moving.
So you are trying to move it.
Yeah, yeah.
Can you try?
I just
Can you try a teleop to his keyboard?
yeah,
From
yeah.
the
I just
terminal?
use this. Yeah, I use this one, my joystick,
Mm-hmm.
but it is not working. Okay, I will test it also.
Oh, there we have Rodrigo, who is having a look to the robot to make sure that everything is fine with it.
Okay.
Or maybe he's rebooting it, or.
The table location is a little bit different in the map. In the map. Anyway, okay, I will.
Okay, so yeah, our colleagues are restarting the robot. Okay,
Okay,
so
still is not working. The tele.
okay. Let's wait for a few
Okay,
seconds. Okay, until the robot
okay,
fully
okay,
restart, and then we can try it again
okay.
in a moment. If you want, you can continue explaining something, and then we come back to this.
Uh, okay, actually, I already captured the video in my presentation,
Okay.
so you can see the
Yeah, sure.
demonstration here.
Okay.
Yeah, this is a application in the robot. The This is the web application.
Mm-hmm.
Okay, start from here. Yeah. Go to the loading position and search the table. Go on the table and then turn to the go out position, turn left, and before the lift up, the centering the robot. Then it will go out to the safe zone. Currently lift up.
Okay.
Yeah, and go out to the safe zone. when the robot is located in the obstacle area, the navigation is not working. So first we have to go out from the obstacle zone. Then move to corridor zone position. Robot sometimes miss the table due to less frictional force between elevator platform and table surface. So the table little bit the increase the frictional force. Yeah, then look lift down and come around and for the go out. Yeah. Then go out from the under the table and go back home.
And you
that's yeah.
You can
Go ahead.
choose where the robot leaves the table, or is that fixed?
Actually, it can selectable, but I have to update code. As I mentioned, the I simulate it, demonstrated the in the actually in the back room that is out of control. I cannot see the robot, so that's why I have to another position to put down position.
Okay.
But it can be changed. You just change the weapon list.
Okay.
Yeah. Done.
Okay, so maybe we can give it a last try if you want.
Okay.
Sanghoon?
Oh, okay.
Or
Okay.
if you want to finish explaining something else?
Yeah, I'm next scenario I would like. Okay. Okay. Let me check. Still is not working.
Okay, let's try something, Sanghoon, because since the robot has been restarted, I would recommend you to disconnect and reconnect again.
Yeah, I just run the tele-op.
No, I mean from the project. So disconnect
okay.
from the robot and reconnect again, or
Okay. I'll try.
okay. Yeah, I think there's some kind of problem from what I'm being told. There's some kind of problem with the robot. These things happen. I mean, when working with hardware, things like this can happen. So
yeah, actually this morning I already checked the operation in your robot. It's working well, but now it is not working.
Yeah. So sometimes, sometimes these things happen with real robots when working with hardware, and it seems there is some kind of problem with the real robot right now. It doesn't look like it's a problem from your code for sure, because we have seen the demo, and also we could see how the path was being planned and everything, but the problem was just that the robot didn't want to move. He woke up lazy this afternoon.
Okay. Should I test tele-op first?
Yeah, just run teleop here directly because it's the fastest. And
Okay.
if it doesn't respond, then we just leave it. At least we have been able to see the demo that you shown to us.
Yeah. Oh, badly not moving.
Not moving. Okay.
Yeah.
So
Okay. I will prepare the demo. Okay, I will show. Yeah, this is the scenario 1 in the pickup table location 1. And then another one is discover the table in the cafe and move it to the put down position. The robot will move around the cafe based on the checkpoint. There is based on the checkpoint, the yellow number 1, 2, 3, 4, 5, 6. Then if the move around this checkpoint, if some place find the table, then go under the table, then go back to the safe zone and go to the put down position P through the corridor position green number 2. This scenario is there. So I will show this demo. Actually, the scenario 1 move the table to the put down position 2. This scenario will discover the table. Where is the table? Okay. Then the robot pick up the table and move it back to the around the position 1. Okay. Send the command discover clean. I mean action. Call the action server. Then go to the checkpoint 1. And then search the table, but there's no table. So the robot move to the checkpoint 2. Yeah. The robot is moved to the checkpoint. When the find a table, then stop, move to the checkpoint, then go under the table.
And how
Yeah.
does it find the table? Using the laser data or?
Yeah, laser data. I will explain it later. Solution detail. Then turn to the go out position. Then center. Yeah. Then lift up. Yeah. Go out to the safe zone. Then go to the corridor position 2, green. Yeah, go to the put down position. Actually, this is a virtual backbone. Then put down the table. Go up to sector. Then go to home.
Okay, cool.
Yep. That's it. Yep. Done. Done. Then now let me tell you about the solution detail. How did I implement it?
You should try to summarize as much as possible, Sanghoon, because we are getting out of time.
Okay. Okay. Normally we set up the navigation to make the map, SLAM mapping, and then localization, and then path planner server computation. Then we can you can see the demo. You can navigation in the environment. This is a real simulation. Yeah. I would like one thing. This is the I mean, this one is the detection system. It's a simulation and real life. The table size is different. So like this, with this formula, I can calculate the width of the table, then detect the table, then approaching the table. Yeah, I use the PID controller here for this parameter. Use this parameter, and this is the approach table. We already see the full scenario, so let's skip here. The move to a background, my the 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 module is a main module is a trash table mover action server. This is some control logic here. This is the my web application. I use the JS and Vue.js and Bridge WebSocket server, and also TF2 web publisher. This is the detailed logic, the end-to-end service flow that you already showed. To see my demonstration, I will skip here. Yeah, this is important. Implement our CI/CD pipeline. It is my focus, main focus, one of my main focus to implement the CI/CD. So when the construct ID Git push to GitHub, we will send the event to the Jenkins and then build the image and then start up the service if the service is running. So I will show you demo, the last one.
Okay.
Yeah, this is this show is the context. The people started with resolution of current context in local WSL2 Ubuntu simulation environment, and trace table cleaner services are running, and the Jenkins server is also running. Expectation is that Jenkins pipeline job start automatically when user execute the git push in remote DB environment. Okay. Yep. So this is running in my local environment. So this is the IDE in the construct website. So user use this git command. Oh, sorry. Yeah, and then git commit and git push to the GitHub. Then the event will send to the Jenkins by local environment. Sometime later, we will get the event. Now get the event from the GitHub, then the pipeline job will start. We can monitor the dashboard or stage view, the overall the progress. You can see there. So also we can check the console output. So yeah. Now the build Docker image. Oh, sorry. And then if the service is already running, so Docker Compose restart the service. So service down and restart the new package will be run. Yeah. And service also run. Installation. So we can develop and also deploy it in simulation or real robot environment. So we can easily deploy it. Actually, I only developer, but we have some team play. Then we can use this CI/CD pipeline. Yeah. That's my CI/CD pipeline implementation. Then wrap up. The Asian lessons learned, I think I have during my project, I faced this kind of issue, but maybe just for your information, I would like to show you the interoperability issue in Docker-enabled Robotic. It could not connect to real robot due to unresolved issue. The solution is that actually workaround. That's why have to be done in my local PC environment. Number two, loss control dependency issue. In Docker image build, during the Docker image build, I get an error message saying hardware name deep drive is duplicated. It makes no sense to me at all. But Alberto guided me through the analysis and solution. Thanks to him. Thanks to you. Number three, real robot malfunctioned frequently, like this situation. The robot I used for my project malfunctioned frequently, so I spent a lot of time to troubleshooting and waiting for it to be fixed. Actually, Rodrigo supported me in this situation, thanks to him also. I think it should be fixed by improving or factory repair, I think. And then here are the items what I try to more study for next step. So study the expanding the CI/CD pipeline stack. So yeah, for example, the Jira and Redmine, and testing is Selenium and TestLink, deploy a Docker registry or private repository. Also, some run related orchestration or Kubernetes, like this. And two is strengthen technology capability to keep trend. The study for enhance OpenCV in robotics. I only study on basic OpenCV in my course, and the study for integration of AI technology to robotics, and also study for private 5G network for robotics. That's my next target. That's it for my presentation. Thank you. Let's have a case session.
All right. Let's do a round of applause for you. All right. So thanks a lot, Sanghoon, for your presentation. It's been very interesting. Many details, many cool stuff. Especially, I liked a lot all the continuous integration and the deployment section that you prepared. Really cool. So yeah, let's do a very super brief Q&A section because we are not going to have time for more. If you want to stop sharing your screen, Sanghoon, so that we can all see you here.
Yeah, one last word I would like to say. I would like to thank Ricardo, who was my advisor and provided me with advice and support during the lecture period. So I would also like to thank Girish, who provided me with support through every checkpoint report, evaluation and comment. And also Alberto, who provided me with advice and guidance, whenever the technical issue occurred. And Rodrigo, who provided support and when an issue occurred with real lab integration. I'd like to thank to you all.
All right. Thanks also to you. I'm going to try to stop your sharing so that we can see you here, Sanghoon.
Okay.
There we go. There we can see you. Let me pin you here. There we go. All right. So yeah, thanks again for the presentation. Then let's try to do a super quick Q&A section because unfortunately we don't have much more time left. Then I have seen many questions in the chat, by the way, many interesting questions. Some of them have been already solved during your presentation. Then let me have a look here. Okay, let me get one from Chris Cool because he has been posting many questions. So, for instance, let me pick. I saw one there. Okay, there we go. So Chris one of his questions was, which navigation SLAM algorithm have you used and which local and global planners have you used? And then I want to extend a little bit this question just by saying if have you done any testing of changing the navigation to planners because of maybe some issues? And additionally, also just to close it, if you have been changing the footprint of the robot from when it has the table on top and when it doesn't have the table on top. So all these questions packaged into one.
Okay. Yeah. I actually used the basic the planner in navigation plugin. So I have to change some parameter for for example the robot move so quickly, so sometimes the robot misses the table because the speed is so fast, increase and decrease. So I have to update some parameter, tune the parameter. And
About the footprint was the other one?
yeah, footprint is also actually implemented because when the robot loading the table, then have to update the footprint because the robot is the table is not recognize the obstacle. We have to change the footprint. So I already implemented it in my solution.
All right. All right. So yeah, you are changing the footprint, and you are using the default planners, let's say,
Yeah,
but
yes, right.
tuning a little bit the parameters for
Yes,
this
right.
specific robot and a scenario. All right, then thanks a lot, Sanghoon, for the presentation. Thanks also for being a great student, and hope you the best in your next steps.
Okay, thanks.
All right.
Thanks.
Bye bye.
Bye.
All right. Then, having finished the first presentation by Sanghoon, let's move straight to the second one. So we are going to change now from completely the topic, and we are going to change also the robot. So we are moving now to Ahmed Mohamed, who is already here, ready to start with his presentation. And his project is there we go. Sorry, I have lost you. So are you there, Ahmed?
Yes, I'm here. Can you hear me?
Yes, we can hear you. We can hear you. All right.
Okay.
So we have Ahmed already here. Let me put you here in the screen very quickly. There we go. Now we can hear you and we can see you. So yeah, as you can see, Ahmed's project is automated shelf detector. He has been working also in a warehouse environment with an RB1 robot. But yeah, let's allow him to explain his project himself. So it's all yours, Ahmed.
Okay, let me share the screen. Can you see clearly?
Yeah, we can see it.
Okay. So, repetitive tasks in the industry are usually prime candidates for automation. Usually, there are ready-made solutions that often address these needs.
Sorry, Ahmed.
Yes?
Can you try to get closer a little bit to the mic, because the sound is not so
How about now?
good? Or maybe increase a little bit the volume.
Let me check.
Now it's a bit better. Now it's a bit better.
Okay. So, as I was saying, repetitive tasks in industry are prime candidates for automation. While ready-made solutions often address many needs, there are still numerous situations that demand the development of tailored custom solutions. Okay, in our case here, we need to automate the delivery of a warehouse shelf, regardless of where its current location, to a specified target location using the RB1 robot. Okay. If we specify the problem is that we need to automate the shelf delivery, and we need to create an app to control and monitor the whole process. We're obviously going to use the ROS and nav2 stack. Okay. If we break down the problem of automation, we can break it down to 3 steps. A search and discovery step, where the robot roams around the warehouse until the shelf is detected. An attachment step, where the robot carefully approaches the shelf and docks under it in order to lift it. And the delivery step, where the robot successfully carries the shelf to the target. This is just for the automation step, before we get to the control and monitoring. Okay, if we take the search step of automation, my solution involved creating a series of waypoints that cover the whole area of the whole area of the warehouse. After starting the nav stack and localizing the robot first determines which end is closer to its current location. After selecting an end, the robot then determines the closest waypoint in the direction of that end. So for example, if the robot is here, this end would be closer, and this is the closest waypoint in the direction of this one. After that, the robot does a full round, starting from the closest one up to the furthest one, while avoiding ones that are not accessible. If the waypoint is inaccessible, the robot quickly iterates to the next one. Now for how the robot locates the shelf. While moving across the map, the robot calls a service with a subscriber that iterates through the laser beam from both ends. So it creates a loop that starts from the last laser beam, and there's another loop that starts from the first one. So it's looping from both directions. And the loop stops whenever a value with the correct laser intensity is detected, because the shelf has special legs that have higher laser intensities than its surroundings. After that, when the laser is detected, it retains the angle and distance associated with that laser beam. Using this data, we can calculate the distance between the two high-intensity beams and verify whether what we found is a valid shelf or something else. This way, something like a single leg or a different object with high intensity can be discarded. We can also triangulate its exact position and orientation relative to the robot. Now we need the robot to attach under the shelf. To do that, I first created a transform between the robot laser link frame and the frame between and in front of the shelf to allow enough distance for alignment. The robot then follows a logic sequence before docking under the shelf, lifting it and backing up. The logical sequence looks something like this. The robot approaches the frame in front of the shelf. Then it approaches the furthest leg until the laser link is centered. Then the robot moves forward slightly to account for the fact that the laser link is not in the middle of the robot. Then the robot can rotate towards the shelf with perfect alignment to start docking. Okay, let me show you a quick demonstration of the attachment process. Wait. Okay, can you see the screen?
Yes, we can see it, Ahmed.
Okay. As you can see here, there's a frame in front of the shelf. The robot approaches the frame until a certain tolerance is achieved, and then starts aligning. This sequence ends with lifting the shelf and backing up slightly. Okay, if we continue to the second step, we have delivery First, we resize the footprint of the robot. This allows the navigation stack to coordinate the robot without hitting obstacles, because now the robot is slightly bigger. Okay. The resizing is run through a service call, and then the robot follows a waypoint sequence similar to the one when we were searching for the shelf, but this one has one endpoint towards the target. Let me show another quick demonstration. First, the robot localizes its location. After it's fully localized, it starts searching around the map. This process continues until the shelf is detected, and then the service for attachment is called. The robot walks carefully towards the target until it's reached, and then it lowers the shelf and backs and walks back. Okay, if we continue. Now what's left is the controlling and monitoring of the whole process. These are the requirements I came up with. We need our application to start the process, and the application should also receive and display relevant information, should stop the process if needed, should switch to manual control if needed, and lastly, the application should be accessible and easy to use. This is the final design. There are 6 main sections in the application: the connection area, the control panel, the manual control joystick, a map with the robot element, a status area, and the log area. Most are self-explanatory, but here are some aspects I think are noteworthy. First, I tried finding a map widget for rows 2 that I can utilize or modify, but none of the ones I found were compatible. I had to build this one from scratch. It subscribes to the map, odometry, and transform topics. It displays the grid cells based on the canvas size, and it calculates the robot's position and orientation for this element here. There's also the joystick widget, which is based on an existing one, but this one is modified to be compatible with touch screens and has been tested on smartphones. I also added a voice control section, or a button for voice control. This button records the audio from the browser when clicked, sends an audio file through a publisher as a string, and the dedicated ROS node receives the string, saves it as a file, and makes an API call to determine the keyword, to determine if any of the relevant keywords are present in the string. The three relevant keywords are search, stop, and return. If the audio contains any of these, the command is sent to the control node. Okay, let me show a quick demo of the application. As you can see, the map matches the robot because it subscribes to the same transform topic. So the map has access to the transform from the map to the robot. Okay, that is all for this. Some possible improvements for the application. Some possible improvements include making a hands-free mode, since the current one requires clicking the button to record every time. The challenge is that trying to constantly recognize audio can add additional overhead and cost. Also, there can be potentially widgets for visualizing the goal path and laser data. Okay, now we can do a quick demonstration with the real robot. Should I connect?
Yes, please, go ahead. Just try writing app at the beginning.
Okay.
It's, that one. Okay. So we are accessing the project again right now. And you mentioned this voice control thing. Is this working with the real robot?
Yes.
Oh, really? Okay, I really want to see that. I think you don't have a booking though, or do you?
Yes, I should do one.
So this is a full live demonstration, even the booking of the robot. That's nice. So can you explain us a little bit, Ahmed, what you are doing?
Okay, I'm confirming that all the files are up to date, so I can launch the process. Everything should be ready now. Okay, there are two dependencies that I need to install for the voice command.
Okay.
That's it.
Does that use some kind of AI?
Yes, the voice recognizer is an API.
Okay.
It does an online call to the API and brings back the recognized text.
Mhm.
Okay, I have now launched the SLAM node and the path planner. Now I'm going to launch the control node. Okay, this has the voice control and some additional utilities for the web service, so the map can work. Okay, everything should be up and running now. I just need the link to access everything. Let's confirm that it's working well. Now to start the search, I could press start, or I could send the voice command for search. This one. Search. Okay, it's working now. You can also see the status here.
Okay.
You can notice now that some buttons are disabled. I could click force stop, but I can't click this now. The robot is now lifting the shelf. As you can see, the robot footprint gets corrected each time the shelf is lifted or lowered down. Now the robot should be heading towards the original position. I think we should have gotten a success here now. Let me check. Returning to home. Last run, success. Okay, now I can use this again. Okay, do you have any questions as of now?
So far, I have some.
Okay,
So first of all, for instance, if we would try to detect the shelf in this updated position, is your system going to handle that?
it should, yes.
Mm-hmm.
Should I start?
Yeah, let's give it a try. So from what I understood, it follows a series of waypoints, right?
Yes.
Mm-hmm.
Okay, now it's detected.
It does this rotation.
Yeah, I think the system failed at this instant.
And the first stop, what does it do? it stops navigation system or?
It stops unless there's attachment going on. The attachment service is disconnected from the app.
Mm-hmm. I receive it.
Okay, let's try again.
The position is correct, at least in the map.
Yes. Please.
Attachment result.
Looks like this is a difficult angle.
It's saying like finish it attachment with card there. Rotating towards park position.
This one is different. This is the one that should finish. It should reach 11.
It seems it's like getting confused at some point, or yeah. Let's maybe give it a last try to see if restarting everything can work. And here we have a question so that you can elaborate a bit more. It's what is the searching logic? The searching for the card logic exactly. So you are following these waypoints and then rotating to try to detect it with the laser, or
no? It walks through the waypoints to walk through the whole map. The rotation only after the detection happens, the robot tries to walk towards the frame in front of the shelf.
Okay. Okay, now it seems like it recovered.
Yes. Let me show.
Yeah, it looks like the robot is becoming a little bit crazy. And also about the voice control, could you show us something?
Try something else. example, I could start and try to stop the system. So the voice on. Stop.
Audio data received.
It should stop after this waypoint. Yes, it has stopped. This is the audio input here.
Mhm.
It published a command of the 0.
And what commands does it recognize?
Stop, search, and return.
Okay.
I could try return now.
Okay, let's try, yeah.
Return. Let me confirm the keywords again. Home, not return. Home. Home. Didn't recognize it. Search. I also think my audio quality is not that great.
It's detecting everything like -1, right?
Yes, -1 is not recognized.
Okay.
Home.
Okay, so okay, let me so because we are running out of time already, Ahmed. So
Yes.
shall we go with the Q&A?
Okay.
Do a couple of quick questions. Let me quickly change here from the screen. Let me give you also an applause. Okay. All right, so we have some questions here. For instance, Girish is asking, can your program search for the card from anywhere in the room or only from a known fixed starting position?
No, it should be from anywhere.
Okay, so you can command it to start the search from anywhere, right? In the room?
Yes.
And Girish also here is asking, how do you think the robot rotation problem can be fixed? I suppose that problem that we were having, that the robot got stuck rotating. Do you have any idea of why that could be happening?
I'm not exactly sure. I tried the search again, it seems to be working. So same problem.
Yeah, there for some reason it starts like doing circles. Do you think do you know or have an idea of what could be going on there?
It should be moving towards a transform between the legs, but somehow the position fails.
Okay. All right, Ahmed. Then I think we are going to leave it here. If you want to say some closing words.
No, that is all.
All right, then many thanks for your presentation again, Ahmed.
Okay, thank you.
Very interesting ideas introduced. I like especially the voice to control. Very interesting idea. So yeah, thanks and best of luck in your next steps. Thanks for the presentation, Ahmed.
Okay, thank you.
All right, then let's give Ahmed another applause. And we are going to move on with the final presentation, which is going to be delivered by Hamza. Let me give him some seconds to join. So with Hamza, we are going to be switching again the topic and the robot. We are going to be moving back to the cafeteria, but instead of the working with the mobile robot, in order to search and pick the tables, we are going to be working with a perception-driven project in order to be able to detect some specific holes in a barista robot, where a robotic arm is supposed to place cups of coffee. But instead of me explaining about it, I see that we have already Hamza here. So let's himself introduce his project. So hello, Hamza.
Hello. Yes. Hello.
Hello.
Can you
Yeah,
see the
we
screen?
already can see your screen.
Yeah.
So it's all yours.
Project, right? Project.
Yes, we can see
Yep.
your project, exactly.
All right. So this is vision guided robotic coffee delivery by me. So the project vision, I'm going to talk about the vision project. This environment is based in a coffee shop. And how this happens is, so basically the user orders coffee through a website and the machine makes the coffee, and then the robotic arm picks up the coffee and places the cup using a vision system. There's a camera there. So the goal of my project is to pick up the cup and place it in the barista robot in one of the four holes. In one of the four holes using a vision system. So let's I'll show you the demo first. So we launch the move group system, and we will then launch the RVs. Okay. And now we have launched the planning scene. So we have the now we launch the hole detection, live hole detection. This I'm using YOLO for detecting the holes. So we launch the system and just give it a few seconds.
Okay.
And as you can see, the holes are all numbered. So 1, 2, 3, 4. It's detecting 4 holes. This is the depth image, just to give me more clarity on the depth. And let's launch the ROS bridge.
So just to give some quick context, right now we are already connected to the real robot. Okay.
Yes, the real robot is based in Barcelona, and I'm in Saudi Arabia. Right. So let's launch the web server. And we launch the web page. So this is the web page. So this is the web page that for this company called Starbucks Copy. And so now we'll take the ROS bridge. We'll also launch the copy handler, right? Okay, now we have to connect to the ROS bridge. Okay, so in the Starbucks Coffee, we place the ROS bridge. We connect to the ROS bridge, and then we have, so basically here we have two menus, I guess. One signature, our signature menu, and special collection menu. These four are for the simulation robot, and these four are for the real robot. So if you see this, so this one will basically go into hole 1, and this will go hole 2, hole 3, hole 4. The same thing that goes over here. So now that we have launched all these files, we have launched the handler file. This is the file that will handle all the launch files. So let's say I want to move it into the hole 1. So the hole 1 will be over here. So here's hole 1. So we special collection, we click order now, and then let's say this one. Yeah, it's launching now. It will move to a pre-grass position,
Mhm.
and it will move down to pick up the coffee cup. Yeah. It picks it up. Then it retreats back to the pre-grass position and moves even higher, just for safety, so it doesn't knock over anything. Now it like this, and go, comes right over there on top of the robot, and then it will go down, move down, and be placed right in this hole. Yeah.
You can see
So
some crazy guy there getting close to the robot, and
yeah,
don't mind it.
and yep, and then you'll open the gripper, and okay, placed in the hole, and now it will retreat and move back to the home position. So, and yeah, that is, and I will just move back to the home position. Yeah. So shall we try another hole? Try number. So and then after that, after it delivers, you get an invoice for you paid. You have to pay $5.99. Proceed to payment, and that's the demo, real demo. So I think we can place the cup back on the. If they can place the cup back on the
Okay.
grass position, I can do it again.
Hopefully somebody is
Yeah,
hearing
hopefully
us
somebody's there.
and they can put.
I think Rodrigo normally is it.
If not, I will go. I can go myself, but I think they are hearing us. Yeah. Or no. Okay, let me go myself in a moment because I'm here also
Oh,
in another room. So no, there we see
oh, Rodrigo is
Rodrigo
there.
appearing
Rodrigo
to
is there.
save the day. Yeah.
Yes.
Okay.
Yeah. We'll launch the coffee handler file again, and we'll connect to the ROS bridge. It's more. It's connected. So now we will put it in 4. Yes. So we'll order iced honey almond latte. So it prepares the order, and it sends the order to the and launches the file. So let's wait for a little bit. Okay, it's again going to pick up the cup. And there we go. Okay, moves up more to a safer position, and then rotates all the way around to cover the robot. Okay, and now it's navigating to the number 4 hole, which is right there. Okay. Yes, sometimes the perception system gets a little muddled because if there's another couple here, it kind of messes up the bounding box around the circle. Explain that. Okay.
And would the system support, for instance, moving a little bit the barista robot down there?
Yeah, that's something that I'll say in the presentation, but it's in the way I have built it, it doesn't exactly support rotating the robot. It just if it's basically because of the frames and everything, it has to be in a structured form, like a parallel form. All the 4. If you put it diagonal, it does not. It does the perception does work, but it's a bit off the x and y the values, so it doesn't exactly doesn't play. So that's a real robot, and now let's continue with the presentation and how I did it. So first, let's talk about we'll talk about the movie 2 setup, then the perception vision system, which has 4 steps basically. We collect and label the images. We generate, train, and fine-tune the dataset. Then we do the live hole detection, and we calculate the 3D point and the transform publisher. The manipulation has 2 steps, the planning scene and the Cartesian path planning. And then I will explain how the coffee delivery process works in the simulation and in the real robot. So this is the movie 2 system. This is just a normal thing that we do. So using this, we use the setup assistant, load the Zagra file, and we set up the joint controllers so that we can easily use the robot arm, and we launch the group, the movie group, and the movie targets. So now we have to collect and label the images. So this is the simulation, and this is the real robot. So in the simulation, I collected about 20 to 25 images, not sure exact amount. I think it's on 23. And in the real robot, I collected about 30 images. And so each of the images, it's in different, the rotated, it's, as you can see here in this GIF, it's all in different positions over here. I had the Hello Rodrigo. And then we label the images. So we label the images using RoboFlow. RoboFlow is, so let me just show RoboFlow and how I did the labeling. Yeah. So if you can see, there is the whole detection for the simulation. It's not loading or something. So let's go into this one. And so basically we just So if you see one of these pictures, for example, it's this one. So this is a picture, and I just drew a box around all of the 4 holes. So I did that for all 30 images. And then I generated the vision dataset, and in the YOLO V8 format, and exported it. And then after that, then we get this one. And okay, after we export the dataset in the YOLO V8 format, we fine tune the dataset. So the dataset is split into 3 different sets: the training set, the variation set, and the test set. 70%, 70 to 80%, 10 to 15%, and 10 to 50% for the test as well. And so then we fine-tuned the data set. So I used around 150 epochs with a batch size of 10. 150 epochs is the amount of times that it will go through each of the images. So the whole process again and again, it goes multiple times. I tried with a lower epochs and a batch size of 8, but I wasn't getting the most accurate perception coordinates. So I had to increase the epochs. But of course, I can't do it too much because then it takes a lot of computer power. And so after the whole data set is fine-tuned, the best weights. So a weight is like a memory for the detection. So basically, it has a memory of how the hole is, and the best weights are loaded into a PyTorch file called best.pt. And after that, we do the live hole detection. So we already subscribed to we take the live image from the camera info, from the camera topic, and we draw an imaginary box around. So basically, then we draw imaginary box around the hole, because we also load the best PT model as it has like a memory of how the hole looks. So it just draws a box around it, and then we convert it into circles to make it look a little better. So 1, 2, 3, 4 for the simulation, and 1, 2, 3, 4 for the real robot. And after we get the image, we have to calculate the 3D points. So so basically in the first step, we draw the circle, and in addition to that, we also calculate the center X and Y of the points of the holes. And then we have to calculate the depth of the image. So basically, we have the center X and the center Y of the hole, but we don't know the distance from the camera to the hole. We don't know where it is. So we know kind of where it is there, but we don't know the distance. So we need to find the distance. So we find the distance there. And then we have to calculate the 3D point, because the 2D point is not of any use. So we have to calculate the 3D point so that the robot arm can move to the 3D point and place the cup in it. So this is the simple formula of the calculating the 3D point. It's we use the camera parameters that's already we can get from the camera topic, and we minus it from the center X and center Y into the depth, and divided by the focal. So this is the focal length, and this is the principal length. And so this is the function that the formula that I use. This is a easier method. Like this is a simple formula, and this is the more a little bit complicated, not complicated exactly, but it's open CV is different one. So this undistorted point equal to CV2 is basically what it does what this does basically. And these two are the camera points. So this is for the simulation, the image raw, which we saw the image raw, and this is the depth image, which able to calculate the depth. And D415 is the real camera. So after we calculate the 3D points, we have to transform them into. So we have the 3D position of the camera frame now. So we have the 3D position in relation to the camera frame. So it's just a point that we have now, and we transform each of the whole points into a whole frame. So basically, whole 1 frame, whole 2 frame, whole 3 frame, whole 4 frame. So all the 4 frames now we have it. These a relative position, and for us to use it, and for the robot arm to move towards that, we have to look up in the world frame coordinates on where these four holes, where these four hole frames are. And then that is those four hole frames are published into the holes detected topic. And so this is how the final detection looks with simulation. And this is the real robot. Right. And this is the planning scene. So we have a wall, the coffee machine, and the table. And this is the robot arm. And so now we use the manipulation, how the manipulation works. So first we initialize the planning scene, and we get the whole coordinates. So the whole file doesn't run without this. So it has to be subscribed to this, and then only when it reads the topics, it will basically all four positions are all four holes are like sent one at a time. So four holes, batch by batch it goes. So we get the whole coordinates, and then we move to the pre-graph position. So this position is already it's already entered by me. Basically, it's already predetermined, and this is also predetermined. So we move to the graph position to pick up the coffee cup. And after picking up, we close the gripper, obviously, we pick it up and we retreat back to the pre-graph position. And then we rotate it all the way towards the top of the barrister robot. And now by using the holes here, we move to the hole using Cartesian path planning with orientation constraint. So Cartesian path planning, we use small waypoints in between every 0.01 step. So to make it more accurate, and orientation constraint, we use that to keep the cup steady and keep the cup straight so that no coffee spills over in a real scenario. And then we move to the hole, again, very slowly using Cartesian path planning. It approaches the hole and opens the gripper, places the cup, and then it retreats slowly. So all of these are using Cartesian path planning and navigation. Navigation completes a navigation path for the robot arm to move, and then we return back to home. And so this is the coffee delivery handler process, how the web page and the robot arm work together, and how that all happens. So this is the simulation one. So for example, you have the spice pumpkin latte and these four orders here. So this is hole 1, hole 2, hole 3, hole 4, right? So when you click order for, let's say, hole 1, right? You click order for hole 1, it sends an STD string to Rossbridge mentioning the drink type and the price, and that is for the invoice. So it sends a STD string message to the Rossbridge, and the coffee order handler file is subscribed to the coffee and orders topic, which contains the drink type. And the coffee order handler file looks at the drink type. And for example, if the drink type is spiced pumpkin latte, it launches the file, the file that does the placement for the first hole. If it's hazelnut mocha, it launches it for the second hole, Irish cream coffee for the third hole, and for the fourth hole, so on and so forth like that. So this file handles all the other launch files. So each of these holes has a launch file of its own. All are basically the same thing, but it's just that so in the hole detection you get 1, 2, 3, 4. So the first hole takes the first hole, the first coordinates that it gets. The second one, it skips the first one, takes the second one, and third one skips the second one and takes the third one, and the fourth one skips all and takes the fourth one. So that's a simulation. And it's exactly the same thing for the real robot, except that it's a different file in the same topic type as well. But yeah, it sends the same thing. So when you press order now for coconut caramel latte, sends an STD message, and the coffee order handler reads this one. And again, even for these ones, there are 4 different launch files. So in total, there are like 8 launch files, 4 holes for the simulation, 4 holes for the real robot. And yeah, that's how the coffee order handler web page works in the real robot. So yeah. So that's my interpretation. Thank you to the instructors for creating this amazing masterclass course. And thank you especially to my instructor, Miguel, who was really, really helpful, and Girish for having patience with me and correcting all my checkpoints, and Rodrigo for helping me, and Alberto as well in the lab. Yeah, it's been a real Real pleasure to do this course, and I've really enjoyed it. So thank you.
Right. Big applause for Hamza. All right, so thanks a lot. Very, very cool presentation. I loved that you started with the real robot demo, starting by the action. So let me very quickly try to send here the screen. All right. And okay. I'm trying to put you here so that we can see you. All right, there we go. Okay, then you can leave your questions for Hamza. I'm going to start by mine. So, first of all, I saw you were commenting also now at the end, and also during the presentation, you showed images from the training, both in simulation and in the real environment. So I wanted to ask, have there been many differences between working with simulation and the real robot, or have you been able to more or less reuse most of the code in the perception part and also in the manipulation part?
Yeah, I was able to use a lot of the, except the camera topics were different. But other than that, most of the code I was able to reuse it. The transform values were a little different, obviously, for simulation and the real robot. But other than that, I was able to use most of the code that I use in the simulation, and the real robot was kind of similar codes.
All right. Let's go. I have another question, and then I will move with others. So, from what I understood, you are sending the frames, these frames of the holes, hole 1, hole 2. You are using these frames as goals for the path planning system, right?
Yes.
Then, so what I'm wondering is why it affects so much the system, rotating the barista robot a little bit, and how could you improve that?
Yeah, that is something that I also thought about. But so I basically, because of all the 4 holes, I published it at the same time. So that's what I'm thinking, that's the reason that it's not very accurate in that scenario. When you rotate the robot, when it moves diagonally, the system gets confused that, like, for example, I have also numbered the holes from top left to left bottom, top right to left bottom. So it gets confused at how because basically it's in a structure, like a grid structure, the 4 holes. So for that reason, when I have rotated the robot and tried to place it, it still does the perception, but the X and Y values are a little bit different and not exactly how you want it to be, and does not place in the hole exactly. Yeah. It's not a huge difference. It's a small difference, but I think maybe you can make that better by maybe adding more, taking more images, maybe even 100, 200 images, and training it heavily, and it will definitely work. But I took maybe 30 images and I trained it with 150 bucks. So maybe even I could have trained it a little more. I could have fine-tuned it a little more to get it more accurate. Yeah, that's the only, I think, the limitation of this project that I did, is that I would have focused more on that. But yeah.
Okay, so in this same line, I want to pick up Girish's questions. He says, why did you choose to use AI, YOLO in particular, for hole detection when you could have used other open CV techniques to directly detect the holes? How is this advantageous? So why did you decide to go for this AI approach, and what was the motivation behind?
Yeah, I had used already. We had used in the course itself, we had used OpenCV a little bit and stuff. So I just thought that using something different like AI would be better. But I could have used OpenCV as well. But I tried OpenCV at first, but I did not feel that it's something that would make my project stand out. I felt that YOLO and AI would make my project stand out more. So that's the main reason that I used AI and YOLO for this.
All right, fair enough. And let's finish with this one also, with another scenario. So here we have one from Miguel. Let me make this one. Would you be able to use the YOLO to detect also the cup on the table if you trained it? This goes in relation also with the last question from Girish, who said, what would happen, for instance, if you send 4 times the same goal? Would it know that there is already a cup there?
Yeah, no. So to answer Miguel's question, no, because it does not, because there is no camera in the real robot to detect the cup. So it has to be a predetermined position. I told Miguel about that it would be better if I was able to detect the cup as well, so that I can be exactly sure of where, because if you grab the cup in a wrong position and then it again, that also will affect the whole placement, because if you grab the cup by half of the gripper, it will not place the cup properly. It'll be a bit weird. And what was the other question again?
Yeah, the other one. So basically, yeah, if the system is able to know that there is a cup already placed in the robot, so if you try to send another coffee there, it's going to tell you, hey, I cannot put another coffee because that hole, let's say, already has a cup.
Yeah, I think if you saw the perception itself does not work when one cup is placed, it does not work in that cup. So only the other holes are detected. But in the system itself, like the live hole detection and the robot, like if I say to move it, it'll probably move. But the perception system itself does not, the bounding box does not come around the hole that is already, the cup that is already placed, or it'll look very weird. It's like a little big. Yeah. But the robot trajectory does not look at anything, does not look at whether whether the hole is empty or whether the hole has been placed. It does not look at any of that, which again, that could have been an improvement as well for this project. Yeah.
Okay. All right, yeah. For what you say, I understand it could be done at least, right? Taking some approaches, it could be
Definitely
done as an improvement. All right, Hamza. So I think we are going to leave it already here. Thanks a lot for your presentation. Let me give you another applause. Also, very well structured presentation and easy to follow. So best of luck from now in your next steps, and talk to you soon.
Thank you so much, Alberto. Yeah.
Bye. All right, then we are going to leave it here. I hope that you have enjoyed the 3 presentations, very different between them, but all of them very interesting. So we are going to come back with more student presentations next year already. This has been the last one for this year, but we are going to continue having in the next months many more students that are going to be hopefully graduating, and they are going to be able to share their exciting projects with all of us. So thanks everybody. I hope that you enjoyed the ceremony, and see you in the next one. And until then, like always, keep pushing your robotics learning. Bye.